Foucault pendulums have been put in numerous places at various universities around the country, actually around the world. And they are one of the tools employed to convince us that the Earth is spinning underneath of us. And it shows that objects, once they're in motion, independent of the Earth, will demonstrate the Earth moving out from underneath of it. They have them in public squares, they have them in university libraries, but they demonstrate for a fact that objects move independently of the Earth, and things, it can be seen when the Earth moves and the object stays on its course. This was alluded to in the movie Shooter, if you saw that, where they were explaining how hard it is to calculate trajectory at long yardages because you have to adjust your aim accordingly to compensate for the rotation of the Earth. There are illustrations that they use to explain this, and they'll show you that you can look down your line of sight and you can compensate for trajectory, but at extreme yardages, the target will actually move out from underneath of the trajectory of the projectile. Here's another illustration of that, where what would appear to be a straight shot ends up being a miss, and your projectile looks like a golf ball that you sliced because the Earth moves out from underneath of it. I'm not going to talk about how this guy did the Red Bull jump and somehow the Earth didn't rotate out from under him. I'm going to talk about something that I know about. I was in the military, in a Ranger battalion, in a long-range reconnaissance surveillance unit, went to various schools, and I've done my share of shooting a lot of different weapons. And I went to a lot of different schools explaining target acquisition. Even after my military service, I continue to be a firearm enthusiast, and I reload my own ammunition, which means I have a very good understanding of internal ballistics. And also, when it comes to in the field, I can use my reticles and calculate yardage and calculate compensation and compensate for the wind quite well. I know how to use a reticle to determine yardage and use that to hit a target in high wind. And at 500 yards, I can yield a target like this pretty consistently. But here's a drill I want to do to obviate the problem with what they teach about the Coriolis effect. I picked Singapore because it's on the equator. And we know that on the equator, the Earth is spinning at about 1,000 miles an hour. There are a few equatorial cities, but this is a good one because it's also on the water. There happens to be a lighthouse in Singapore also, which makes an excellent stationary target. This is called the Marina Lighthouse in Singapore, within 1 degree of the equator. So let's bring in the shooter who's going to hit this target. Meet Mr. New Jersey. This is one of the biggest battleships ever made. It has a 16-inch gun that can reach 25 miles. I've seen specs that say up to 28 miles, depending on the ammunition, but here's a quick snip of some proof. They're saying that bullet actually goes almost 2,700 feet per second, and here they claim 24 miles. I've seen different ones. The weight of that bullet is a ton. Here's a picture of an old decommissioned barrel with a mock projectile to give you an idea of the size of this gun, because this is what we're going to hypothetically set up as a scenario to hit that lighthouse. Here's one of the projectiles in the magazine tube where it would feed up to the gun, and once it gets up there, they pack hundreds of pounds of powder behind that bullet. It's one of the more impressive guns anyone could ever see fired. When they pull the trigger, the explosion is so enormous that it sounds like it's the end of the world. When you see them fire them off from the air, you can see the decompression of that barrel gas make a shockwave across the water the size of a football field. So you aim at your lighthouse 25 miles away, you pull the trigger, boom, it should fall to the ground, right? Well, not exactly. We got a couple problems with this, and let's use math. 25-mile target from the New Jersey has a flight time of 90 seconds. So you're aiming 90 degrees from the ship straight to the equator to hit that lighthouse, and it takes 90 seconds for the bullet to get there. Problem is, in 90 seconds at the equator, the Earth moves 25 miles. So it takes 90 seconds for the bullet to get from the ship to the lighthouse, but in that 90 seconds, the lighthouse moves 25 miles. So you're going to miss it by 25 miles. Now, those are nice numbers to work with because it sets up a triangle. And you can do a little math to go, well, could I actually lead the target and compensate for the Earth spinning underneath of it like they say you have to? Well, how far is it? A squared plus B squared equals C squared, which will give you the distance of the hypotenuse you would have to use to lead the target at a 45-degree angle. And you'll find that you couldn't hit that target because it ends up being a 33-mile hypotenuse. So you're going to shoot a lighthouse. The ship and the lighthouse move. Even if you tried to lead the target, you're going to fall 8 miles short because the range of the gun is only 25 miles. Think about that, people. I don't think that this ship misses targets. I don't think it's 25 miles off when it shoots at a target 25 miles away. You have to use your brain and just think about some of these things that obviate that they're full of crap. They show you Foucault pendulums and say everything moves independently underneath of an object, but then they tell you this guy floated around for hours above the Earth and jumped in the same place he took off from. You have to analyze and think on your own, and you just tell me if this makes sense to you, because it makes a lot of sense to me. Hope you have a great day.